energy so that we can focus on these correction terms that I have mentioned.
Oh, sorry, can I interrupt just real quick?
Yes.
So it looks like we didn't quite go live just yet, so I want to actually just rewind this real quick to the beginning. Sorry about that. So welcome, folks that are attending our streamed version of the undergraduate research talks for our space physics and astronomy programs. We have some very talented students here today that are going to be talking about their specialties, that are going to be saying some very interesting stuff, and you have the opportunity to interact with them during that time. So if you have questions, if you have curiosities about their specialties, and if you're watching this live, you are welcome to interact with us in the YouTube chat, that YouTube chat section of the video. You can ask your questions. We'll be looking at that area, and potentially we'll be posing your questions to these talented students for them to answer at the end of their talks. So with that being said, thank you again so much for coming by, and let's get started with our very first program. Each of them is going to be about 5 minutes each, and we're going to be starting with Jennifer James, a junior in space physics, who's going to be talking about the short-range gravity tests of Lorentz invariance.
Thank you, Eric. So yes, my name is Jennifer James. My mentor is Dr. Q.G. Bailey, and together we are studying short-range gravity tests of Lorentz invariance. And so I wanted to go over the purpose, the actual way we're going about this. So we want to examine corrections to Newtonian gravity caused by an underlying unified theory of physics that may break Lorentz invariance. And this can be done using the standard model extension framework. And results from this can be used in short-range gravity experiments such as HUST 2011. So HUST 2011 was developed by Dr. Xiao in Wuhan, China. And so this experiment basically takes two test masses, two counterbalances, and it tests for local Lorentz invariance violations. And that's one way of going about testing for Lorentz violations. And so first I wanted to go over the Lorentz invariance itself. It is one of the fundamental symmetry of relativity, and it is the cornerstone of general relativity and particle physics, in which it states that the outcome of a local experiment is independent of its velocity and the orientation of its laboratory/experiment. Which leads us to the unified theory of the standard model extension test framework. And a quick definition is that is a general theoretical framework for testing relativity based on the action principle. So this includes general relativity plus the standard model plus correction terms. These correction terms are what we are looking at today, and they are a dimensionless coefficient for Lorentz violation. They are fixed constants, and they stem from a fundamental theory of physics. And so the basic idea is that we have space filled with one or more background tensor fields that may interact with this matter. And this is the image that I have pulled up here today. And so we're going to look at this here example. So Dr. Bailey and I are analyzing the potential force between some mass and an infinite circular plate with respect to a coefficient S sub q. Now, where did S sub q come from? We'll see here we have a modified Newtonian potential energy with some coefficient S sub jk. S sub jk is a traceless, dimensionless matrix, and we derived S sub q from this matrix. And so we are looking at a special case of one non-zero coefficient, and we see here that there appears to scale the usual result in Lorentz invariance that we have indeed an explicit Lorentz invariance breaking. The same example can be seen here, but with a square plate. All that changes is the way of evaluation and computation, but we derive from the same traceless, dimensionless matrix, and we receive another Lorentz violation breaking. And so for future plans, we hope to look into higher derivatives of the Laplace equation and to delve and experiment with those. And these are my references, and that is my short little talk on Lorentz invariance and short-range gravity tests.
Well, thank you very much. That was a great talk, and we have a bunch of support for you in the chat right now. We don't have specific questions, but we have wonderful support. I have from Noel Richardson. He's saying, "Good luck, everybody." There's a lot of people that are familiar faces. We have Nora and Brad in there. So thanks to them for showing up for this event, and also encourage any questions people might have as we wander through these presentations. Next, for our presentation on the list, we have Ashley Elliott, who is a senior in space physics. We'll give a couple of minutes for setup for that time, and we will be right back for that presentation. Welcome back. We have our next presenter on the docket. We have Ashley Elliott here investigating large planet candidates.
Thank you, Eric. All right, like Eric said, hi everyone, my name is Ashley Elliott and I will be presenting on my research project over the summer with NASA Goddard. I investigated large planet candidates around M-dwarf stars. All right, so this summer what I did is I worked with the Transiting Exoplanet Survey Satellite, or as I'm going to refer to it as TESS throughout the rest of the presentation. So during the TESS's primary mission, TESS observed M-dwarf stars, or low-mass stars, in large quantities. And M-dwarf stars are really, they're in large quantities in the universe, and because they are so small, relatively small compared to the sun, planets are a lot easier to detect around them. So you can see this in the figure on the right over here. We have a star about the size of our sun, and we have a little planet trying to go across it, and down here is a very, very shallow transit right here. But if you take the same size planet and put it in front of an M-dwarf, the transit is a lot deeper. So transits in front of M-dwarfs are about 25 times deeper than that of a star like the sun. And so most planets also around M-dwarf stars are relatively small as well. So they range in size from about the Earth to about Neptune. So large planets like Jupiter or larger are very rare, very uncommon, with only 5 known Jupiter-sized planets around M-dwarf stars being discovered by TESS, ground-based observations, and other missions in the last 30 to 40 years. So what I did over the summer is I used the Python light curve package, and before that I looked at the ExoFOP catalog for exoplanets, which is basically this huge database with all of the stars and exoplanets that we think exist in the universe right now. And I narrowed it down to focus on just M-dwarf stars and then also planets 5 Earth radii or larger. And from there, the light curve package was used to create and examine light curves. From here, any light curves with interesting features were singled out, picked out, and investigated further. So here on the left, you can see some really, really pretty light curves. It is a phase-folded light curve from the ExoFOP vetting documents, and these documents were used to further investigate all of these planets. So my results, basically, I looked at 52 candidates 28 held up to further investigation. Among these 28 were some really interesting systems. Some notable systems include several candidate planets larger than Jupiter, which I will talk about in a later slide, a star that has sunspots, flares, and a planet transit, which can be seen in this lower right plot right here. Right here is a ground-based observation light curve. This is a transit, and then right over here is a really cool flare. And then up here is just a really very nice image of a star with a planet, and that's what we look at for further observation. And lastly, I found a triple star system, which possibly has a planet transiting in front of it. We don't know. We need further observation. But it also could be an eclipsing binary system, transiting with the planet transiting in front of it, or just 3 stars kind of circling each other and doing their little dance in the universe. So here, more about the triple star system. So over here is the TESS image. So it's very low res. It's really hard to see really what's going on. This yellow square right here in the center and this red dot, that is the star that we are focusing on. But this image right here is the speckle image. And so this is a high resolution image, and the way that the data is processed, it flips and mirrors the image. So the actual stars are these here, right here, and right here. So it looks like there's 5 stars, but there's really only 3. And then over here is a beautiful little phase folded light curve, or transit of the planet, or what we think is a planet. But this curve does lead me to believe that there is a planet transiting in front of one of the 3 stars in the system. We are just unsure of which one it is transiting in front of. So finally, to conclude, I investigated giant planet candidates transiting low mass stars from TESS. And I found 28 systems that held up to all of my further analyses and tests. And this plot over here is a plot of all of the planets that I focused on. All of the green dots are all of the 28 candidates that I looked at. And the red dots, you can see a couple here, here, and here, are the 5 confirmed Jupiter-sized planets around M-dwarf stars. And so, as you can see, if any one of my planets are confirmed to be Jupiter-sized or larger, or really if any of these planets in general are confirmed as exoplanets, it's going to further our knowledge of planet formation and planet occurrence around M-dwarf stars. And thank you very much, and I will take any questions.
Fantastic. Excellent presentation. We have more comments of support. We have somebody with mysteriously the same name as you, Carrie Elliott, saying good luck, Ashley. I think that's a great sentiment. And I guess I have a question myself, which is if you had any and all resources in the world, how do you think you would like to have this project continued, either by yourself or by whatever team would take up the mantle?
So currently, I am still working with NASA Goddard and my mentor, Dr. Joshua Schlueter, on this project, and it's kind of as I can. And so currently, we are trying to get some proposals written to use ground-based telescopes to further investigate some of the really interesting candidates, like the triple star system, and the really clean light curve that I showed you a couple slides before. And so with those ground-based observations, the telescopes can observe the stars, take data, and basically just monitor the stars and see and try and confirm if there's actually a planet in front of them, in addition to also using other satellites and telescopes that are currently orbiting our Earth right now, like TESS, try and use TESS time to also continue, and then also just trying to reach out across the world to find other ground-based telescopes.
Yes, let's make astronomy universal. So thank you very much for your presentation. Following this will be Emily Strawn, so please stand by for just a minute or two, and we will be right back. in space physics presentations. And you know, I think there are some people that are just made to be in certain degree programs and certain jobs. Here we have Emily Strawn, who is in the degree program Astronomy, I just love that, and is a senior in the program, who is here to talk to us about hydrogen emission variability in Eta Carinae. Sorry to interrupt. Can you press up the button on your microphone?
I'm so sorry. Is that better?
Yes, I think we may want to restart here, but thank you again, folks. We have live experiences which include technical difficulties, but I think that's part of the organic fun of the situation. So once again, we have Emily Strawn, hydrogen emission variability in Eta Carinae.
Thank you again, Eric. Sorry about that. Once again, I'm Emily Strawn, and I'm studying the hydrogen emission variability in Eta Carinae. This is research which I began this past summer with my mentor, Dr. Richardson. So just to begin, I'm going to go over some basic facts about Eta Carinae that are a bit relevant to my research. You'll probably hear a little bit about this from Connor and Alexis as well, who will be presenting after me, just because they're also doing research on Eta Carinae. So Eta Carinae is a binary star system inside the Carinae Nebula. Inside the Carinae Nebula as well is the Homunculus Nebula, which was formed from a particularly large eruption in the 19th century. So this eruption left a large amount of gas, which formed its own nebula embedded inside of the Carinae Nebula. Also to note is that this binary system has a particularly large eccentricity in its orbit, meaning that the stars start fairly far apart and then transit really close together. So this creates some particularly interesting win-win collisions as the secondary star passes by the primary star relatively close. They have some, the winds coming off the stars collide, which create this sort of shockwave pattern of a less dense cluster of the gas. So the research I specifically am doing is all with data which is collected during the periastron events. The periastron event, of course, is when the two stars are closest together. So I'm looking at the hydrogen emissions, which are particularly interesting because it is the strongest emissions from Eta Carinae. They also are strongest where the gas cloud around it is particularly dense. So if you go ahead and look up here real quick, you'll see that this plot I have displayed shows a P Cygni absorption characterized by a strong decrease followed by a strong increase, which is exactly as we would expect due to these win-win collisions as the gas cluster is becoming less dense and more dense in certain areas. So as well as just looking at the data itself, I also am comparing the data to previous cycles. This helps not only confirm past results, it helps gives us an overall image of the evolution of the system. So by looking at all of these small snapshots in time, we're able to see how it's changing, what helps us figure out how it's going to be changing in the future, as well as how it may have changed in the past. So we're able to rewind time, which helps gives us an understanding of not only how this system is changing, but how other systems similar to it may be interacting. So if you go ahead and once again look at this plot I have displayed up here, you'll notice that these two plots have fairly similar trends. This top one up here is from the 2020 periastron event, and the one down here is the 2009 event. So you'll notice that they both have a decreasing line strength until it reaches a minimum, and then it increases slightly and levels off. And they both have their minimum, which is during the periastron event. You'll also notice, oops, sorry about that, there we go. You'll also notice, which I find particularly interesting, and maybe one of the most interesting points about these plots, is that the line strength from the 2009 event was significantly stronger. So it started all the way near 700 angstroms and decreased down to near 400 angstroms, whereas this last 2020 event started in between the 500 and 600 angstroms and decreased to similar levels. So that significant difference is something that we've seen in past observations as well. So I know there was a 2003 event, which was noted to have a similar trend where the minimum was near periastron still, but it was significantly weaker than the one before it. So this is all very interesting, and I find this particularly fascinating just because I'm able to be witnessing Eta Carinae as evolving as it's happening. So I'm able to see all these different little pictures of it in time, and I'm able to witness this story, which I find extremely cool. And thank you for listening, and thank you for your time. Do we have any questions?
Thank you for a most excellent presentation. And we are continuing the trend of the chat for this YouTube Live program being just barrels and barrels of support. From Noel, we have, "You're doing great, Emily. You got this." And so I am going to expect from the chat, I'm putting expectations on you now that I'm seeing this trend, that for each person we're going to get wonderful comments of support, and at the end I can tell them those comments. If we get questions, well, that is just gravy. But I am expecting support now that I've seen it already. But yeah, thank you again for an excellent presentation. And next on the list, we have Connor Pickett. We will be right back with his presentation in just a couple minutes. Please stand by. All right, folks, welcome back. We are still here in the midst of our marvelous astronomy and space physics undergraduate research presentation. Next on the docket, we have Connor Pickett, who is a senior in astronomy, and we'll be talking about some very strange, some bizarre sodium absorption in Eta Carinae.
All right, thank you, Eric, for that wonderful introduction. As you said, I am talking about bizarre sodium absorption in Eta Carinae, which you just heard Emily talk about. So some background on this bizarre absorption. In previous research in Eta Carinae, we have noticed a cloud of stellar ejecta in our line of sight, which means that there is a very large cloud of dust and gas that is obscuring our direct line of sight for Eta Carinae. And because of that, there are sodium absorptions, which are absorbed by the cloud, and that is what we see in spectroscopic readings. So when sodium absorption comes through to our spectroscopic readings, we notice that the absorption component at negative 145 kilometers per second is stronger when the two stars at periastron are closer together. And over the past couple of years, so notably in the 2009 and 2014 periastron passages, we have recognized that the sodium absorption lines are actually getting weaker. But that is not the most interesting part of my research, although that is what we initially thought would be the most interesting part. So in May of this year, I started reducing, normalizing, and cleaning 2019 and 2020 periastron data that we received from the CTIO telescope in Chile. And through that, using Python and Jupyter Notebook, I was able to compile GIFs, like the one that you see here, of the data that we received from Eta Carinae. And this data shows the two absorption lines, one here on the left and one on the right, and that is due to sodium being one of the elements that creates a doublet in wavelength readings, which is very bizarre on its own. In June of 2020, I created more plots, but converted them to velocity readings of Eta Carinae's spectroscopic data. That spectroscopic data in velocity allowed me to recognize two very weird, bizarre sodium absorption lines next to the main absorption. So right after the huge dips from sodium absorption, there were two smaller dips. And those were previously unrecognized and not any sort of absorption that had been noticed by even NASA before, which was quite interesting. And those told me that they were very small sodium absorptions, but I could not exactly tell what was going on with them at the time. So in July and August of 2020, I reduced, normalized, and cleaned 2018 data from CTIO to see if these absorptions were continuing from previous years. And it was interesting enough that they actually were. And to analyze those more, I measured, and analyzed the bizarre sodium absorptions using various methods, being velocity, width, and depth. And those absorption lines created these plots. In 2018, you see that the absorption fit curve depth has a particular straight trend, which means that they are relatively constant. And then 2020, you see that again, and there's a dip here, but that is not present on the 2018 one simply because of a missing data dump that we were not able to retrieve. And then further analysis on those, with a better fit curve depth, you see another straight line trend, and that continues in 2020 as well. So this data told us that these absorption lines were not something that were relatively new, but that they were continuing from previous years and previous periastron events. Future analysis on this topic will include receiving and analyzing Hubble Space Telescope ultraviolet readings, which will help us compare and better understand why these sodium absorptions are occurring. And from that, I will compare the Hubble Space Telescope data with the 2020 and 2018 data that I have previously analyzed. And that'll, again, help tell me if these absorption lines are some weird occurrence, or if they're consistent through all of Eta Carinae's lifetime, or if they're something that should be characteristic of any binary system that we recognize in the universe. And we are going to be testing hypotheses as a team for what these sodium absorption lines are. But currently, the leading hypothesis of these weird sodium absorption lines are that sodium is actually falling back into the star system, which in and of itself is a very bizarre occurrence, considering that there are strong stellar winds blowing material away from Eta Carinae. And that tells us that this is something that probably shouldn't be happening, but it is, and we would love to look into it further. So that is my presentation. Thank you for listening, and I will take any questions.
All right. So excellent presentation on behalf of Connor. And we are continuing the trend of wonderful support and compliments, particularly in this strangely coincidental way. A lot of people seem to share the same last name as the presenter. I'm not sure what that's about. But we have a Megan in there who's talking about, well, just loving the presentation. And in text went into a bit of an Arnold Schwarzenegger impression that I'm going to try my best, but it's not going to be very good. But go Connor was essentially what was said there. But yes, great presentation, and we're going to move forward next with Alexis Lane, who will be back with her presentation in just a couple minutes. So stay tuned.
slides up.
All right, welcome back. Once again, we have more presentations. Today is just a great day for all the astronomy content, all your astronomy needs. Next, we have Alexis Lane, who is a junior in astronomy, talking about helium variability in a system, hey, we might have heard from before. There's a bit of a trend going on here, but let's see what's going on.
All right. I'm Alexis Lane, and I'll be talking about helium variability in Eta Carinae. You've heard a lot about this already from Emily and Connor, but all right. So what is Eta Carinae? So Eta Carinae is a massive binary star system, about 40 solar masses, and it's undergone 2 eruptions. The Great Eruption in 1837, where it outshined just about every other star in the sky, and then another smaller eruption in 1890. It's expected to go supernova at least once in the future. So what I look at are the helium-1 lines. These lines are due to stellar winds. There's 3 lines that I look at, 4713, 5876, and 7065. And we're looking at these lines at periastron, which, like Emily said, this is when they're at their closest point. And this occurs about every 5.5 years. So at this point, there's the most variability that we see. And I'm measuring the p-Cygni absorption, which is another absorption component right before the emission lines. So what we do is we use a Doppler shift to find the velocity, and we can measure the velocity and depth of these absorptions and compare it to other periastrons. And so using this lovely equation, we can fit the absorptions, as you can see. And from that, we can find the depth, which this is from the 2019, 2014, and 2008 data. What we've seen is that there's more absorption in the past compared to now. And then here are the velocity comparisons. So moving forward, we're going to begin looking at the helium-1 line at 4686 angstroms, which strengthens at periastron and a little bit later on. This line corresponds to hot massive stars, and we're hoping to get more information about the companion star from this. And that's about it.
Thank you for that presentation. And you know what? We're going to buck the system. We have a question for you. Please, everybody, stay in your seats. Don't fall over. So we have a question saying, at least once, can it go supernova multiple times, was the question.
Well, the things that I was, like the research papers and stuff, made it seem like I guess it could. A lot of them were saying at least one supernova. I'm not really sure. That's not my exact focus. I'm more focusing on the emission lines.
Well, that's mystery there. And also, not bucking the trend, keeping with the trend, we have incredible words of support from everybody. There's people that are shouting for the Eta Carinae team. There's people in the comments mentioning that, hey, maybe the professor that is leading this does study other stars too, but you are all doing great on this star, so why would he have to bring you into these other stars? But thank you again for that presentation, and we're going to head right along, keep on trucking. So next, we're going to have Lauren Perez, who will be coming at you in just a couple minutes, so stay tuned. And welcome back once again. Thank you so much to all of you who are staying through and hearing this interesting diversity of presentations. Before we get on to the next one, we have a development in the chat I just wanted to mention, is that there was that question initially asking if this system can go supernova multiple times. And Noel Richardson was mentioning that it is a binary star, so both stars can explode. So that is for your reference there. And now to proceed with the presentation itself, we have Lauren Perez, a senior in astronomy, estimating the time of shock breakout in core collapse supernovae. So staying on that trend of star explosions.
Thank you, Eric. And once again, I'm Lauren Perez. My mentors are Dr. Michele Zanelin and Dr. Noel Richardson. So in my research, we are estimating the time of shock breakout in core collapse supernova. So what are core collapse supernova and how do they work? Well, this occurs in type 2 supernova. And for this, we're going to look at this image over here and focus on the core of the star. So first off, the core will undergo fusion and that will create that iron and nickel core. This will cause the core to collapse on itself, as we can see in these two images right here. And that collapse will result in an outward shock wave. So that's represented in red right here in these two images. And that will expand, and eventually the shock wave will reach the surface, and that's when the light will become visible. And that is what we call shock breakout. So we are trying to estimate the moment of shock breakout from an incomplete electromagnetic observation of a light curve. And right here is a really good example of a light curve. So going over that, right about here is where there would be a gravitational wave detection. Then right here where we see the graph rapidly go up, that's the shock breakout. Then here, that is the actual time the supernova would have been discovered. So our methods. We want to estimate this by including a theoretical curve and experimental data. And we want to see how well they match up. So in this image right here, the dotted colored curve represents real data, our experimental data. And the curve in the back is a theoretical curve created by a code I will go over in the next slide. We also have been looking at some papers that include analytical models that have good representations for this for about the first month of the supernova. So as you can see, this model is accurate right up until about here, which is about a month. So some information on the supernovas we are using in this experiment. These supernovas are from Kepler, and they are 2011A and 2011D. 2011A is smaller than 2011D, but it's closer. And what makes these so special is that they both went supernova in Kepler's view. And 2011D is even more special because this is the first time we have been able to capture that shock wave in visible light. So this animation kind of shows what that would look like. As you can see right about there, that would have been the shock wave. So some issues in my experiment. I was first given a code when I first joined the team, and basically I had to learn how to run that to create those theoretical curves. And basically I can put in some parameters from the progenitor stars such as mass and radius. And there are some more parameters right here. Then we also need to decide how to create a best fit. And we want to use the experimental data instead of best fit for the experimental data instead of relying on that theoretical curve. And for that, we've just been doing some derivations to create that best fit. Then we really want to understand the uncertainties that come with using data from the telescopes. So the relevance of this all. Once we get a good estimate for the shock breakout time, that'll narrow down our interval of time where we believe there will be the gravitational wave emission. And this will decrease any false alarms, so once we have a detection, we'll be able to trust it a little more. And that is all for my research. Thank you for listening.
And thank you for telling us about it. Yeah, we're just going to continue with this supportive atmosphere from Jordan. We have a go, Lauren, very enthusiastic. So everybody is very happy to be hearing about all this. So thank you, students, for what you're doing. And following this presentation, we have just one more left. Will you stay till the end to see what's going on? I hope you do. Please stick around. We'll be back in just a couple minutes. And for the last time, how bittersweet. Welcome back once again. We have a presentation to end the pack by Coulter Richardson on gravitational wave memory from asymmetric core collapse supernova, and he's a senior in space physics. Take it away, Coulter.
Awesome. Thank you very much, Eric. Again, my name is Coulter Richardson, and I have been working with Dr. Michele Zanlin for the last, I want to say 3.5 years now, doing research. But our most recent project has been investigating gravitational wave memory. I'll get into what the memory of a gravitational wave is momentarily, from asymmetric core collapse supernova. So Lauren already discussed briefly what a core collapse supernova is. It's a really, really big star, usually bigger than about 8 solar masses, that eventually gets too big for its own good, doesn't produce enough energy to keep fighting all of the material that's trying to slam its way into the star, so everything falls in, hits a proto-neutron star, or it's just a star that's made up of a bunch of neutrons, really small, really neutral atoms that, or not atoms, particles that don't do anything. So when all this material hits it, it bounces off, explodes into the atmosphere, and then we get the beautiful shock breakout that Lauren was discussing. So why are we interested in supernova with respect to gravitational waves? All of the detections that we've made for gravitational waves so far using the LIGO detector, and we now have on the network as well Virgo in Italy and Kagra in Japan. Why are we interested in these things? From core collapse supernova. Well, in core collapse supernova, we've got a lot of energy that starts building up in the system and starts exploding out into the space around the star. So this gravitational wave memory is the gravitational wave from the energy of the supernova that comes specifically from the asymmetric explosion itself. So asymmetry, core collapse supernova, they really don't explode in perfect spherical balls every single time because there's a lot of really, really complicated hydrodynamics, magnetodynamics, all sorts of things that start influencing the way the star is going to explode. As we can see in the picture, this is a simulation done by Dr. Sean Couch at Michigan State University. This explosion is happening in a prolate kind of direction where all of the matter is either going up on the z direction or down in the negative z direction. But realistically, these aren't the only kind of models that we have. My research specifically with Dr. Zanlin is presenting 3 models for these core collapse supernova. The prolate, which you just saw, an oblate, which is more of a frisbee. It's a disk where all of the matter just kind of goes out on the equator of the star, and a spheroid explosion, which is much closer to a perfect sphere, but we have parameters that we can change how tall it is, how wide it is, and we can actually vary those to get different results. Using a simulation done by a group in Germany, we use the W15-2 model. I'm not going to get into that other than it's a 15 solar mass star, so it's got 15 times the mass of our sun, and it isn't rotating. Why that's important, we won't go over in this presentation, but for our model and for our simulation, we see very clear patterns that actually emerge. In that figure, on the top, we see the simulation of the H plus and the H cross. These are two independent gravitational waves that come through, and they just distort the time and space in different ways. On the bottom is our simulation of those gravitational waves emitted at the same time that the simulation ended. And at least to me, it looks like we've got a pretty good match. We can model the mass of our explosion and the velocity of the final material as it spreads out through space. And by modeling these and picking the exactly perfect explosion direction, we can get very similar explosion dynamics. Why is this important? Well, gravitational waves are the new multi-messenger astronomy expansion. We are seeing optical detections that we have from all of the Eta Carinae, the binary people. This is the telescopes that we actually physically see what's going on in the universe. We have neutrino detections, which show us what kind of really high energy mechanics are happening in very, very dense areas and very, very energetic areas. And now we have gravitational waves, which gives us an example of both of them. We can see those explosions be in their asymmetric geometry. We can see how the neutrinos are interacting with the matter. We can see how just the star explodes using these gravitational waves. On top of this, gravitational waves are detected in, again, I mentioned LIGO, Virgo, and Kagra, the United States, Italy, and Japan. And these detection curves show us the prospects for actually detecting this gravitational wave memory. This gravitational wave memory isn't really detectable in current detectors. It's hard to see. Depending on the distance, we can actually get some nice signal-to-noise ratios. But at 10 kiloparsecs, or roughly, I don't know the exact scale off the top of my head, but 10 kiloparsecs, which is what we assume to be the average distance, we don't expect to see these. However, in future detectors, which are going to be shown on the very far, if I'm looking at this, the left side of the presentation, this very low frequency region right here, we see that our gravitational wave memory, the orange and blue lines, is well above these purple and green and pink lines, which says that we're going to get a detection most likely. These are in future detectors, so we're looking at the 2030s for these guys. In conclusion, gravitational wave detectors probably won't detect a core collapse supernova memory signal for our current detections unless they're really, really close to us. However, if a GW from a core collapse supernova with memory is detected, we can actually, using our methodologies, describe the mass, the velocity, and the general geometry of the explosion. And through these techniques, we have actually discovered that the gravitational wave memory is linearly polarized. That's got a lot to it, so I won't get into it. But for gravitational wave detectors, their analysis actually has programs, has parameters that we can put in that will make our detection easier, given a morphology like a linear polarization. So we are working closely with the LIGO Virgo Kagra collaboration and trying to implement our morphology, or implement our methodology to better detect this gravitational wave memory. There's all the image citations and the simulation that we used. Thank you very much.
All right, thank you for that most excellent presentation. And to continue on with the overflowing of support, we have a good luck from Michael for you. And I want to talk to everybody who's been watching. Thank you for coming forth for this experience. This is the first time that we've streamed these research presentations live. We'd love to hear what you think. And I also encourage you to head back into the chat that was happening live as well, because not only do you get to hear these students talk, but they're the people in charge of their research, those professors, those guys were in the chat and they were answering questions. So you get to hear different levels of specialties, and I think it was a great experience. But yeah, once again, if you have any thoughts about what we did now that you really liked or things that you'd like to see more, please do contact us. You can give us comments. You can also email us at prplntrm@eru.edu. That is the planetarium email, prplntrm@eru.edu. Thanks again to these students, these talented students, for their excellent presentations, and thank you for watching. Have a good rest of your day, and we hope to see you again at a future streaming presentation.